Hi folks, it's Alan here and I'm in my electronics cave again, and I'm delighted to say I've just finished working on this thing. This is a slightly longer format video explaining a little bit about what's going on in this BNC detoxifier and reclocker. Now this is specifically designed for a customer who has a Chord MScaler and a Chord Dave DAC, and apparently the MScaler is a great piece of kit, but unfortunately it does generate quite a lot of electromagnetic interference, and that impacts the DAC and impacts the quality of the DAC. So what I've built here is something that's designed to take in the input from the Chord MScaler, which is in this case two BNC inputs, completely clean it up, reclock it and spit it out before it goes into the Chord Dave DAC. And actually, after all of this is done, theoretically you should have a signal that is so much cleaner and so much more precise than the original. So let me describe a little bit about what's actually going on in here, because there's quite a lot to talk about. The first thing that you hit when you come into here is the dual channel BNC receiver chip, which you can just about see here. There's this little chip there. Now that chip basically just receives the BNC input, but even that in its own right requires a little bit of power. And remember, this is noisy power. So what I've done here is I've taken power, clean, quiet power from a linear power supply, and then filtered the bejesus out of it using inductors, capacitors, and actually I've completely electrically isolated it using DC to DC converters to totally eliminate any ground plane crosstalk. And so what this does now is this basically means that this little section of circuitry, and actually up to and including this bit, has its own completely separate and completely isolated power supply. So great, I take in the BNC input, I convert it to some nice signals that I can handle quite nicely in here. But because of, and ultimately then, I'll talk about this section of the circuitry in a minute, but what I then do is I pass it through a series of opto-isolators. So I completely optically isolate the signal as well between the input stage, which is the bit we're talking about here, and the final output stage. The downside with using optical isolators, though, is that they do have a tendency to introduce jitter. Now, these are high-speed opto-isolators, but even so, they do introduce some. So what I've decided to do in this is actually, in the final output stage, to eliminate any jitter, I'm completely reclocking the signal as well. And that's where the clever bits and actually the difficulty comes in this particular design. Because reclocking it needs me to do several things. I need to generate, first of all, a clock that is completely in sync with the input. And what I've got here on my trace here, as you can see here, the top line actually is the input signal. This is coming from the BNC input. The next line down is actually the output signal, which I'll talk about in a bit. And the bottom line here is the clock that I'm using to completely reclock that. And you'll see that the clock is in phase and synced with the top signal. Great. Okay, so how did I do that? There's multiple stages to this, but essentially this needs to handle lots of different frequencies, everything from 44.1 kilohertz right the way up to 384 kilohertz or even 768 kilohertz signals. And that's a problem because most of these standard chips don't cope with that. So what I've done for the kind of lower frequencies up to about 96 kilohertz, I've used a pretty standard DIR 9001 chip here, which is an SP diff receiver chip. And great, okay, that gives me a nice clean clock for those low frequency signals that I can do something with. But unfortunately it doesn't work for the higher ones. So what I've had to do here is use this particularly obnoxious beast, and I have to say this was an absolute nightmare to solder because that chip package is 5mm by 5mm and there's 33 pins on it, so that was exceptionally difficult to handle, and all of those pins are all underneath it as well. But that does for the higher frequencies what the DIR 9001 does for the lower frequencies. It ultimately just gives me 3 signals that transfer through into the rest of the signal. I've got BNC input number 1, BNC input number 2, and a clock, a completely clean clock. I'm only using one of the BNC signals, but there's BNC input number 1, and there's the clock. Great, okay. So, I've got those signals. Surely I could just pass those to the output. Well, actually that's not good enough. First of all, the clock that I've generated at that point is good, but how good is it? It's low jitter, but it's only low jitter relatively. Plus it goes through optical isolators, so that actually introduces the jitter a bit further. So what I've done here is I've built a completely new reclocking circuit here in the second half of the circuitry. And this uses voltage-controlled crystal oscillators and a very, very heavily slugged phase-lock loop chip here that's designed to then sync one of those two clock chips, depending on whether it's a 44.1 or a 48 kilohertz base. It syncs one of those two clock chips with this clock that's coming in via these optical isolators. And it syncs it very, 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 very closely, although it does actually allow that clock to just jitter ever so slightly on the input, which means that the output can be maintained absolutely, completely, and totally jitter-free. And I've done that by using a phase lock loop, with a low pass filter essentially between there and the control inputs on those two voltage controlled crystal oscillators, and that allows me to very, very slowly adjust the frequency of those crystal oscillators to bring them into sync with the input, but not adjust it so quickly that it will introduce jitter. So great, I've now got an extremely clean clock, and the extremely clean clock then basically sits in this section of the circuitry here. Now, as a slight extra complexity, there's a couple of chips here that are actually designed to detect whether it's a 44.1K or a 48K base signal, and that's needed because the two crystals, the two base crystal frequencies that you need for those two are different, so I need to be able to select which one of those I'm using, and for those I'm using that, and effectively this little LED down here actually tells me which one of those signals I'm synced with, so great, all of that's working really quite nicely. But then what I do is I then take the clock, so I take the two digital input signals that route all the way around to this chip here, which is a D-type flip-flop, basically effectively a buffer, and I'm taking the brand new clock signal and I reclock it at that point. So I clock that signal out into the BNC output only when I want it. And that means that ultimately I end up with the second trace down here, which should be, and if I just stop this briefly, you should see it's basically an almost identical version of the top trace, but just delayed ever so slightly because it has to go through a whole bit of the circuitry. And importantly, the rising and falling edges on that are absolutely precisely aligned, not with the top signal, but precisely aligned with the clock at the bottom, which is a very, very clean, very jitter-free clock. So ultimately what I end up with on the output is an extremely low noise output with virtually no noise, and actually don't worry about the noise that you can actually see on here. That's because my oscilloscope at the moment, I'm getting nasty noises being fed back in by another circuit that's connected to it, but you'll have to trust me that is extremely clean, and there's no higher frequency components, and also it's all clocked using this almost perfect, almost jitter-free clock at the bottom. So yeah, I'm thinking this is a great result, and I'm really looking forward to seeing how much the customer likes this. Fingers crossed.